organized for. Okay, so welcome to the first sort of substantial lecture. It's about the attractor dynamics approach toward vehicle path planning. I'll also start introducing a little bit the basic concepts of planning and some general things, and then we'll dive into this attractor dynamics approach, which gives us also the opportunity to talk about the qualitative theory of dynamical systems. The dynamical systems tutorial that I uploaded in connection with the exercise one. I will not give that formally, but that provides a lot of the material. So now we'll be discussing this in this concrete context of path plan. So let's just first think about, by the way, the slides are already online. So if you want to follow in the PDF, you can follow that. So if you think about sorry, I have to move here this bar out of my way here. So, okay. The general problem, now what does it mean to do vehicle motion? It means moving in a plane in 2D. Of course, in the real world, there could be inclines and so on. So the surface could be complicated, so we're not into that here. And generally, when you move as a vehicle, the main idea is that you have a target, a goal to move to. That's the only way a task comes into a system like that. And the only major constraint is that you avoid collisions with obstacles. In general, there would be additional things like following a particular route, like on a road, and there might be maybe via points you have to go through. Like if you're a vehicle in a company, you would have certain via points you have to go through and so on. And these will not be the things we'll be discussing. So we're really just discussing about the planning action of a vehicle that consists of going to a target while avoiding obstacles. So it's the most basic planning problem. It already spawns a lot of literature. There are lots of approaches about that. And I'll spend the first, I think, 3 lectures about that, about different aspects of that, and present here one particular approach. So I mentioned via points here. So docking behavior, I'll make one point in a moment about that. So it's one thing to be at a particular location. The other is to maybe park at a particular orientation. Now that would be docking. So so in light of what I reviewed about autonomous robotics last week, this problem entails multiple different layers in a sense. It entails, of course, knowing something about the environment, so about where the target is and where obstacles are. And then it entails planning the movement in that environment that leads to the target, collision-free movement. And then it entails control that is ultimately physically bringing about the movement. And it will, which itself will entail some form of estimating the state of your vehicle, for instance, estimating whether you achieved what you were trying to track, and then maybe keeping track of that. So I'll focus in this lecture only on the planning part of that. I'll make some trivial comments about the 2 lower levels. We're returning to estimating the vehicle state in 3 lectures down. We'll talk about navigation, estimating where you are in the environment. I'll not really say much about sensing here, even though I have this one lecture on SLAM, self-organized map formation and self-localization and map formation. Again, I think 3 lectures down for me. So to put that into perspective, in the sense plan act picture, this would be this level, right? We talked about these different layers, and that's how it's often conceived. And a lot of the literature approaches that I will be reviewing are of that nature. What I will be talking about this week and next week is actually ambiguous. I will present it here in this lecture as if it was part of that. That is, we get some parameters that would be from some world model or some perception process, and then we'll only deal with the planning and then hand it down to the controller, and we'll not say much about that. But in the lecture that follows, we'll use the very similar math to do something that's closer to this, and you will see that, where there are special purpose sensory information that don't require actually estimating something in the world, that are really call that low-level sensor information. And the same math will actually be able to work here. That's how we've actually used this approach. So these are 2 steps. The first, and we've actually made hardware demonstrations of both kind of approaches. So even though it's the same equations, they can be used in these 2 different senses. This will become clearer once we've gone through the first approach. To further position this, I wanted to mention a few concepts for such path planning. So if you read the handbook article or some literature, you will often see reference to these basic concepts. So it's just to position itself. So for planning, it's also true for more complex action planning like that of robot arms. One distinguishes between local versus global planning algorithms. So local planning algorithms are the ones that use the sensor information that is directly available to the autonomous robot, to the vehicle, based on its own sensors at a given moment in time with a given field of view. See, that's very relevant for vehicles, because when you're somewhere else, you don't see the same parts of the world than in the original location. For robot arms, this might be less obvious, even though there can be similar cases, similar problems where, for instance, you might be looking around. You have a camera that scans the environment, and you're not always seeing everything. Yeah, and so tendentially, what we'll be talking about is a local approach that just uses the information directly sensor already available. To make it global, you would have to do something like build a map or have some external representation of, once you will take a case where you know where the target is based on mapping. So you don't see the target, it's just you can say where the target is, even if it's not in view. A related difference, some of these differences are not, they're mathematical limit cases where they can be well defined, but some of them are a little bit vague actually in the literature. And this next one, reactive versus planning, I think isn't really totally clear. So reactive is typically thought of as being local and therefore reacting directly to sensor information you have there live. So it's a notion that it is real-time sensor information that isn't integrated or stored in memory. And it's also very typically thought of as something that is using direct strategies. So it's not using complicated optimization of something. Versus planning. Planning is everything else, and so planning is sometimes thought of as devising an path or an entire action sequence that leads to the goal, which would then be acted out, and then you actually have the problem of revising the plan if, as you actually execute it, you find out that maybe you didn't quite achieve the goals of the piece of plan you executed, or the environment changed. But it's not really always that way. So just put that out there, that you're aware there's a whole spectrum of terms. So a lot of people, especially those who are biologically inspired, use the word planning more loosely. So plans that can be updated anytime. Then it's not really so categorically different from, for instance, a bit more reactive.
Excuse me.
Yes, please.
Yeah, I had a question like, what is the difference between the local versus global? Like for a robot, if a robot is working in a warehouse, so for that, the local and the global might be the same thing, that it's working in a warehouse. But for a drone, it might be a little bit different. Like it can go from indoors to outdoors. But for a robot, it is, if for a warehouse robot, it is in the warehouse itself. It will not be operating in the outside world. So what is the difference between local and global in this reference?
Good question. So local really refers to sensor information. So if you're in a warehouse, for instance, local might mean that you have a depth profile. And let's say in the ideal case, you might have a 360-degree depth profile. So you know how long flight of time of your sensor until it hits the surface, but you don't know the layout of the warehouse. So if anything is occluded, because there's a wall, there's a door you have to go through, or there's some objects that occlude something, then you don't know what's behind those. So you would be always planning just based on what you currently see. And that makes, for instance, not obvious how you achieve going to a goal if you don't see the goal. So this doesn't matter if it's indoors or outdoors. Drones have this sort of bird's eye view, and everything that's within that view would be their local the local data. So anything that's just depending on that would be local planning. But again, the view might be limited as maybe certain viewing angle, and the objects that are outside that view would then require global information. Typically, there is an aspect of global in most of these planning ideas in that you're assuming that you can move toward a goal that you don't have direct sensory information about. See, if the goal is already in view, not much of a drive. It's kind of very simple. But some approaches, like the ones we'll be discussing, reduce that information just to know in which direction the goal lies. You might like have a compass, for instance, and I'll illustrate that. And then it's local in a certain sense, even though maybe you get that information from having actually global information, that is having a map and knowing in that map where the goal is, and you're estimating where you're in that map. But for instance, in many cases that we've been using, that information doesn't have to be very precise. You have a rough idea where the goal is. And then when you get close enough to the goal, it might come into your sensory reach, and then you start to really use a local approach. Okay, yes, please.
I guess building on that question, I was just wondering, so would you say that these different approaches, they pair better with each other? So like, for instance, a local approach would be much better with a reactive sort of thinking?
Yes.
Or would you say that they can be mixed and matched, or does one type fit the other better, so to say?
Well, very often local approaches are then actually realized as reactive, and people who say reactive often mean also local. So that is actually just different terminology sometimes used. The local versus global has been mathematically studied in certain abstractions, and that's where that terminology comes from. The reactive term is more like from certain architecture, so more applied kind of term. Yes, and very typically these things are mixed. I had that slide, I think, in the introduction talking about hybrid architectures, and that is sort of the state of the art that is most current robotic devices, even arms, have what they call a deliberate planning. So it uses AI and symbolic representations to do sequences of steps in some plan that will be global and planning. And then they have a reactive planner for the details, for the exact steering, and that would be local and use real-time sensor information. Yeah, the other set of concepts is also from this theoretical literature. I should say there was a whole wave when this started, like in the 60s and 70s, when autonomous robotics started. There was a lot of theory work and really mathematical theories, proving theorems, like idealizations like polygonal worlds, and then can you find a path, under which conditions does one exist, is it unique, and stuff like that. And so exact approaches come from that sort of literature where there is some formalization of what an environment consists of and what it means to, what a plan mathematically is. And then exact would mean that if there is a possible path you find, either it's not exactly found, you actually find it. That would be an exact approach. Almost all approaches are horizontal. So they use that to prove theorems, and this is a whole line of business. I'm not sure today if this is really used in practice. Almost all approaches that are used in practice are called heuristic approaches. That is, they are techniques that will tend to work, but you cannot actually guarantee that they work in all cases. You can create situations where they don't work. So initially there was a lot of concern about this question of exactness until sensory information became good enough to actually do this work, and then the problem was really much more that whether they have good sensory data than whether your approach is exact or not. So the approaches we'll be talking about are always heuristic in that sense. And then there are a lot of approaches that are categorical in nature, that is essentially searches on graphs. For vehicle planning, this could be that you have a set of via points that you just planning the set of movements through that. There's actually some evidence that animals do stuff like that, and I will return to that when I talk about navigation. And there is a lot of mathematical framing this way, while the continuous form of planning would be to do that in a continuous state space where you're planning position or you're planning velocity. We'll essentially talk about these continuous ones more extensively. We'll talk now about a velocity-based one, and then I'll talk about the potential field approach, which is position-based. And only I will refer to these graph or grid-based approaches only a little bit more, less technically, so just reviewing it in like 3 lectures down from now. So that's a bit the framing of that. And so I will be presenting a local, reactive, heuristic, and continuous approach in these terms. That's what we call the attractor dynamics approach. So we developed this, some of my doctoral students, we started this work actually when I was here in Bochum 30 years ago, more than that. And it was actually based on analogies with human behavior, which I'm alluding to a little bit later in this talk, even though actually it was the other way around, the data came after the model, but it was by analogy with other things than navigation. It was actually analogies to human movement coordination, and there's a whole, sometimes called some dynamical systems thinking, a whole idea that you would account for the organization and coordination of movement by postulating that movement emerges from dynamical systems, so the different parts of your behavioral system contribute different forces in a way, different contributions to the dynamical system, and then the stable states would be the correct behaviors. Using that analogy, we developed this for robotics. I knew very little about robotics, especially it's not shot in the dark. Only later we discovered this whole literature. It's a bit naive. It turns out that there is a literature that we can connect to. I'll review that a little later. And then we actually really developed it as a robotic approach, and we did a lot of work, went to conferences, presented this, and so on. It's not an approach that is standard or very often used. There are a few labs around the world who use it. There is another approach, a potential field approach, which is used much more. I will review this also in an upcoming lecture, even though this approach is much better, actually. And the reason why it's not used so much is probably it's mathematically a little more challenging. And I think it's really just that. I don't think there's any good reason that it's not used much. And I have only worked for a few years in robotics, and most of my work is then in cognitive science. So I didn't push this very much. There is a modern branch of this that for arms, where it's much more used, because say vehicle planning is also in some sense solved, and so people are not so interested in it anymore. While in the control of robotic hands, when timing is important, like catching something, that people are really using more advanced versions that are based on this. And in fact, they do reference us. Good. So it's a little bit special. It is more, I will show in the second part of today's lecture an application to human movement. And that group is frequently cited. And so this work is quite prominent in that area. And it's all based on our approach. But now the guys who did the experiments are more frequently cited. So you don't see that it's exactly that, but it is actually exactly those equations. And they cite us correctly. So it's, you'll see that a little later. It's just if you Google this, you will see that it's more that work that is visible now, because I haven't really kept working on that either. Good. So basic ideas of this in a summary, and then I'll step you through this. So the idea is that you're developing the plan as the time course of particular variables that I would call those behavioral variables, just some fancy term, but we could also say the variables in terms of which the plan is written down. I'll explain that in a moment. And these time courses are generated by as solutions of a dynamical system for a differential equation. And they are really solutions in the sense you have that equation on your robot and you're solving it numerically on the robot. And the parameters of that equation come from the sensory information that you have. And they are organized by attractor solutions. That is the thing that you design are stable states, attractor solutions. And then in practice, the system isn't always in the attractor, but it's close to the attractor. And that's what I'll show you. And these attractors will bifurcate sometimes. That is, there are instabilities. We'll discuss that, what that means. That leads sometimes the system to make decisions. Now, in the introduction, I mentioned stability, attractor stability is the same. Stability really means small change in input gives small reaction. And decisions are points where small change makes big reaction, like small change of the position of the obstacle will maybe trigger going around it on the left rather than on the right. That will be a decision, very simple. And we'll actually discuss exactly decisions like that. So I'll step through these points and it will become clearer. Yeah. First, I should maybe say a few things about these variables. Vehicles have actually 3 degrees of freedom. So degrees of freedom for the physics and engineering or mechanical engineering are variables, mechanical variables here that you can choose freely. You have some initial conditions you can choose freely. If you have an object like that, how many degrees of freedom does it have? Anybody knows? How many? Yes?
So we can rotate it on a vertical axis, then on a horizontal axis, so 3.
3 rotational degrees of freedom. And 3 translational, because that would have 6, right? The rigid body. When you constrain the rigid body to a plane, it turns out that you have three left. The position are 2, and then there is the orientation, right? We think of the system as just like a disk, right? The orientation, so it's only 1. It's a bit odd. It's 3. So 2D position and 1 orientation equilibrium. There are special non. Yes, please.
6 or are there more?
So 6 is just mathematically or physically the degrees of freedom of a rigid body. And we will be studying the degrees of freedom robot arms when I talk about kinematics in the second half of the course. And we'll then actually argue that robot arms consist of many rigid bodies chained together. And these chains and the joints restrict the degrees of freedom, typically to just 1. A hinge joint has just 1 degree of freedom. And so typically you will have a robot that has actually 6 rigid bodies, each one restricted to 1 degree of freedom through that hinge joint, so that together, again, they have 6 degrees of freedom. That's most robots, like industry robots. Experimental robots and more advanced human-like have then more. Like we have 8 degrees of freedom in the robot we have downstairs. And then there are more fancy kind of robots that have a lot of more degrees of freedom. And that's a whole topic. I will talk a little bit about that in the second part about redundancy, having more degrees of freedom than you need. Yeah?
How many degrees of freedom does a human have?
That's a nice question. So we're really interested in stuff like that. So talking about the human as a sequence of rigid bodies, right? If you just talk about the bones and the joints, we have something like 80 or so joints. It's actually a little bit ambiguous because you have things like the spinal cord and there are a couple of, the back, what's it called? The spinal cord is this thing inside the vertebrae, where it's a question, how many degrees of freedom does it really have? Because it's sort of, some of it is passively, it's elastic, but it's a restricted freedom. But something like that, so less than 100. But that's still quite a lot. We have about, I should know that number, but it's like maybe 700 something muscles. So if you think of the muscles as the actuators, multiple muscles per joint in a way. So that's about that order of magnitude. So that's still considered a lot. And there are people who are trying to design robots that would go in a direction like that, like having fingers and not so successful at the moment. Boston Dynamics is famous. They have these humanoid robots, and they have sort of the main body degrees of freedom of humans, inspired by humans. But we have, of course, also things like mastication, the whole mouth area, and we have most of our head, and what else counts? We have a complicated hip, yeah. So I think they have maybe like 20 or something like that. So they have a lot more, some subtle ones. I can't even remember all of them now.
The tongue as well.
The tongue is actually, exactly, it's not a rigid body. It's like a continuum. Yeah. It's just one muscle. I don't think it counts in that count of joints. And also the eyes, right? The eyeball. So Good. Actually, in the second half, of course, I'll talk a lot about things like that. Okay, so this is much simpler. This is why we start here. So it has 3 degrees of freedom. It has a special feature. It is what we call non-holonomic constraints. That is, there are fewer variables than the number of degrees of freedom that can be varied freely. That is, when you're if you're going to a particular, so this is a bit different. So our depends on the robots that we'll be looking at. You can actually rotate them on the spot, and so they really truly have 3 degrees of freedom. That is, you can freely vary these 3 positions. While if you have an actual vehicle, it can also be positioned anywhere in the plane in any orientation, but you can actually only, at any instant in time, you can only vary 2 things, and that's the parking thing, right? And some of you might be familiar that it's not always so easy to get the robot to be in that orientation that you want, like parallel to the curb, right? And that's what is called a non-holonomic constraint. That is, there to achieve the 3 degrees of freedom, you have to have a particular history of getting there, because you actually only 2 degrees of freedom are freely available at any moment in time. So for instance, in a car, you have the steering wheel and the gas pedal in a way. These are 2 degrees of freedom, right? You can move tangentially forward, back and forth, and change the curvature of the instantaneous angle. But you can bring about that it has a 3-dimensional configuration, right? If you take into account the history of the parking. So that's actually an interesting topic. There's a whole literature on that. Autonomous parking was one of the challenges. Most cars, these advanced cars, have actually autonomous parking algorithms. Some of them are so good that it's difficult for a human then to leave the parking spot when it was autonomously parked. So I'll not go into that. Just gloss over that. So when you're thinking about these kind of vehicles, we'll be talking about only 2 control variables. So we'll not actually address the docking behavior, which would be this orienting the vehicle, right? For the non-holonomic cars, it requires a whole set of maneuvers. For these kind of robots, well, when they have arrived, they can rotate into the right direction. This, for a circular robot, it would be even true if you really have to dock, like you have to approach something from a particular direction, because you could just go there and then rotate into that direction and go straight, right? And we actually build concretely robots that are circular in nature, and it's very easy. And that's one reason why they are like that. Yeah, and other people worry about how to do that more generally. Right? Actually, a lot of the robots that are used for these kind of purposes are spherical. And sometimes they are squares, but their mechanics is actually spherical. They can rotate on the spot. So the variable we'll be using most of, actually, I think in all of the lectures, I only talk about one variable, but in all the papers that this is based on, there's a second one. So the one variable is what we call the heading direction. Heading direction describes the instantaneous orientation of the velocity vector, which, if you think of the path, it will be the tangential vector to the path. And that instantaneous angle is against some arbitrary but fixed world axis. And so, for instance, if you had a compass, it would be against north. That's actually how you navigate as a sailor. I actually was a sailor in my youth. I was in the Navy, and I was actually a navigation officer. I really worked on that. So I actually really manually did this estimation with the angles. I might refer back to that when we talk about navigation. Navigation normally is knowing where you are, right? And this is not going somewhere. So it's a very common variable. Now, we don't actually require the vehicles to have a compass. Typically, they don't. And it doesn't actually, it turns out it's not a variable that really needs to be calibrated. You don't really need to know exactly how it's defined. You will see later that it's mostly differences in that variable that matter. It's just that the miscalibration of that variable shouldn't drift too fast. If it drifts as fast as you're moving, then you don't know what's going on. But if it drifts a little bit more slowly, then it doesn't really matter. But mentally, We'll come back to that. That's kind of an important thing, it turns out, that it is relative to a fixed world axis. So in particular, it's not an axis that's on the robot, right? That will be rotating with the robot. It's when the robot rotates, the axis relative to which you're measuring its orientation remains fixed. So think of it as a relative to north to make that mental picture easy. So the other variable is the forward velocity. And so if you think of a robot with active wheels, the one is essentially a function of the difference of turning rate of the two wheels. If the sum of the turning rate of the two wheels is 0, then it's rotating on the spot. And the speed is the average of the turning rate of the two wheels. And there's some coefficients in there that have to do with how large the wheels are and how wide the vehicle is, right? That's in practice, all the kinematics. If you do a robotics lab class, you will have one task where you have to figure that out. It's very easy, simple thing. So I will be neglecting that other variable. We will often just assume that you have a constant speed. You're just driving with a constant speed. Typically, in our autonomous robots, we drive more slowly when we're close to collision, which makes a lot of sense, and I'll discuss that occasionally. It also makes sense within the approach why we would do that. So let's now talk about the heading direction. The other thing is, again, 2 lectures on when we talk about navigation, I will actually argue that it's a really biological variable. It turns out that the animal navigation behavior can be very well described. Mostly it's rodents that are measured this way. And there is a variable, it's actually in the literature, somewhat ironically, it's usually called head direction, not heading direction, head direction. So it's actually the orientation of the head in the world. And that's because in the laboratory, that's what you can actually easily measure. However, a freely behaving animal of this kind, a rodent, will typically move in the direction which its head is pointing. So it follows its head, right? It looks ahead in the curve. Of course, it can occasionally look around, but it overall does that. So it's actually probably a good proxy for heading direction. And the biological structure that is involved in that is very likely responsible for planning the motion in terms of the body's orientation in the world, the path in the world. Okay, that's heading direction. That will be a very important variable we'll be using all the time. It's important to wrap your head around. So here I assume this is a fixed axis. This long green thing is sort of giving you the forward direction, the nose of the vehicle, right? And it's mostly important because the motors would be on an axis that's orthogonal to that green axis, right? And that would explain that if we're not talking about this control level, you know, but that typically we'll assume that there are, maybe you say this one word about control, we will assume that there are, I think maybe I have a slide about that. Yeah, I'll come back to that in a moment, sorry. Good. So this is a good variable because the constraints that we want to fulfill here in planning can be expressed in terms of that variable. So here's a sketch of that. So if you have a target somewhere, you could say the constraint of going to the target can be expressed as a desired value of that heading direction, namely the angle under which the target appears from the arbitrary world axis. That would be the heading that you want. If your nose is pointing in that direction, then you're going to the target. That will be this directional sense. So if you're sailing, you have the compass, and you're saying, if my target, in German we say Peilt, you know, if my target has this or that pylon, and in English would be the bearing, right? You saying my target's from 10 degrees from north, then if you're steering a course of 10 degrees of north, then you're heading right to the target, right? And again, it doesn't really matter. You see the world axis, if you should shift that loads on both the heading of the vehicle and the bearing, and therefore the difference is the same, right? So it doesn't really matter in which reference frame that is. For obstacle avoidance, you could say, well, maybe there's a certain direction in space in which I'm detecting an obstacle, and that direction can be characterized therefore by this angle toward the obstacle. It might be typically a range of angles because my obstacle might be a whole region in which there are objects. And then that's a range of values to avoid. I don't want to go in that direction. You see immediately that this isn't good to do very rigidly, because if you avoid any direction in which there's something, right? Then you could only navigate if it's an infinitely free space, right? So there will be some modulation with how long that distance is to that obstruction, and we'll come to that. But we can express these two constraints in terms of that variable. If you have a time, yes, please.
The world reference axis, is it fixed on a point, or is it always on top of our robot and just points always in the same direction?
So in practice, that axis is implicit in the code that you're writing. So we will not typically calibrate it. And so if you so in the code, you use some variables that will turn out in many cases, you don't even need to estimate your current heading, but under some circumstances, you need that. And that will mean that when you put the robot down in the world, there will be a world axis. Depending on how you coded that, it might be an axis that's orthogonal to that initial position, or it's ahead. Depends on how you wrote down the code, where your angles begin and end. And then as the robot is moving around, that axis remains the same, except that the fact that the robot makes some errors might make that in reality, the axis that is implicit in the variable that it has inside might be slowly becoming decalibrated. So after some driving, the robot might think that the zero axis is this direction, while actually it's been shifted a little bit.
But the origin point, like 0, 0, is also at the same spot? Or
yeah, the origin of that frame is in the robot. So it's local in that sense, right? It's an orientation in the world. But it's not actually, we're not tracking the position of relative to some, it's not with respect to translation, it's only with respect to orientation, that this axis is relative.
Okay.
Yeah. Which is what a compass does, right? It tells you an orientation irrespective of where you are. Except, on the Earth's surface, there will be some complication, but locally, it's a translation invariant. Okay. So if you have a time course of heading, and assume you have some speed, then you can see the path emerges from that, right? It's just time series describes the path and the world. You could compute that, and imagine x. The x component will be the sinus, or x will be cosine, I guess, depending on how you define that, cosine of that integrated over time and with the velocity and the speed, and the y-axis will be the sinus of that. So it is uniquely defining the movement behavior in the plane. It's also, we call that inactable. So strictly speaking, there is a concept of controllable, but that entails more things than I'm describing here. But it's at least intuitive that you can realize that path. So in practice, in terms of control, right? In practice, what all of these robot vehicles do is they have servo motors. There's nothing better than servo motors. So servo motors have some internal sensor, different kinds that estimate their rotation rate or even their positional, the position on the axle. This can be some like little a disk that has some encoding where you count how many holes there are, some sensor for that, or other techniques for that. And they have a control circuit. I'll discuss a little bit control in the second part of the course for robot arms. So some control circuit that the voltage sent to the motor is tuned depending on the rotation rate or the position of the motor axle that then achieves really a desired speed or position. And very good in the sense it's very well developed technology, thousands of things. Every garage door is a thing like that, right? Every model plane is something like that. So it's very common because they charge you more if you buy it for a lab, but in general, it's a very standard thing. And so that means that you can make sure that any desired rotation rate for the vehicle's wheels can be realized by the wheels. Now, there are limitations, of course, if the vehicle is also a mass, has inertia. So it depends on how strong the motor is, whether that control is sufficient to do that. If you make a weak motor on a heavy vehicle, it might not be able to do that. That's by design. You're not designing the vehicle this way. You're not giving it too much payload. So you can eliminate that problem. The other control problem is, of course, that the contact between the wheel and the ground is not guaranteed to be that way. And so when there is any kind of slip, and for actual cars on the road with uneven ground, that's a real issue. And that is then a control problem, how you do that optimally, especially go around bends, and there are complications if you have. These robots are ideal because their rolling condition isn't violated, as you might know, for some for actual vehicles with more complicated geometries. The rolling condition is violated, so there's some friction, and the wheels always slip a little bit, and so on. And so that's what the control guys work on, how to do that optimally and so on. So we'll neglect that. Is we'll say in a good approximation, this can be controlled. That is, if I have a certain heading direction and a certain speed, then I can realize that speed. It turns out that a lot of the approaches we're talking about have some kind of closed loop property. That is, if I consider that heading direction time series to be the plan, and I notice by sensory information that now the target is somewhere different from what I thought, because I didn't actually follow my command, it can update that plan, and that would go in the direction of also stabilizing my behavior. I would, for instance, still go to the target because the target angle changed as a result of me not actually achieving what I wanted to achieve. So in that sense, this is open to being in control. But most of these ours and a lot of other approaches don't really formally analyze the stability as a control problem. It's separate work where they do that. And those people, of course, who do that with actual cars and vehicles really spend energy on doing that right. There's a lot of stuff that I gloss over here. It's just the planning part. Okay. So this, I already said that, so I'll now step you through the different stages, the different logical steps of how to make this time course from an attractor dynamics. So that begins softly, but it becomes, in a way, you'll see it becomes not terribly complicated, but sort of pushes the limits of maybe the math that you're familiar with. Okay, so target acquisition is, in a sense, an easy thing. It's sort of a control-like problem. That is, we're saying, okay, we want to have a heading direction that is located where the target is detected in angles. So what I need to do is erect a dynamic system, like a control system that has a attractor there, a stable fixed point. That is, I define a dynamical system of heading direction. So this is heading. This will be the derivative of heading as a function of heading. If you have a variable and there's a functional relationship between the derivative of that variable in time, or the rate of change, right, and that variable, that's called a dynamical system. And you hopefully reminded yourself of that in exercise 1. And a fixed point of that dynamical system is a constant solution of that, right? That is, if your heading is exactly at that value, then your rate of change is 0. And so you're going to go straight. You're going to stay on that heading. So the solution where that remains constant is a solution of the dynamical system. And if you arrange for the slope of this dynamical system to be negative around that fixed point, then it's an attractor or stable state. It will simply mean if you're heading a little bit further to the right, you have a negative rate of change. So your angle will decrease. You will go, turn more in this direction, and keep doing that until you're here, and then you go straight. And if you're a little bit to the right, you have a positive rate of change, so your angle will increase, and thus you're sort of sucked into that, So in engineering, you would do this with a linear function. This will be a linear function, and you call it a P controller. It will be a D controller, a differential controller, because this would be the distance from the desired state that you would be controlling. And so it would be just a straight line with a negative slope. And remember, in engineering, the negative slope is usually expressed as the real part of the eigenvalue, because it would be a multi-dimensional system. The real part of the eigenvalue has to be in the negative half plane, of the imaginary plane. So I'm just alluding to those who know that sort of stuff, right? So this is really analogous to that sort of idea. Here is a nonlinear function, really, just because it's an angular variable. So angular variables have to have periodic solutions. If you don't do periodic, somewhere there will be the transition from 0 to 360, and the dynamics is supposed to go smoothly through that because it's the same point. So a linear function would make a jump there, right? We don't want that. So we'll use sinusoidal functions or sinus and cosine functions and so on. So in practice, this contribution will very typically be a sinus function, actually a minus sinus to have the negative slope that then connects. So in the sense, you will have a repeller, I said ahead of time, in the opposite direction. Now, away from the target, there will be a heading where you are also fixed point, but with a positive slope. So if your target is behind you, there's a repeller here. So I'm a little bit to the right of that, I go this way around to the target, and a little bit to the left of that, I go that way around to the target. And so that's a simple decision, but a very special one, right? Because it just happened to head exactly in the opposite direction. This is actually a relevant case. A lot of these sort of model cases around which planning algorithms have been evaluated are certain special situations. This is sometimes called the chicken cage. I don't know why it's called the chicken cage, actually. So where your target is, like you have a street, but that's blocked. And the target is sort of behind that block, right? And you, a naive controller would just go in that direction, then be stuck. And so you'd have to drive against that direction for a while to get around, right? And that's sort of that pushes the constraint, the conflict between the two constraints of avoiding the obstacle and going to the target. And a lot of local approaches might have a problem. They always go in, then they see it's the problem they go against, but then if they're far enough, they try again and so on, and they get caught in this kind of situation. And so we'll come back to that later, how to escape that. Yeah, so that's, you see that already. So it's in a sense like control. You have an initial heading, and then you will go to the attractor, and then you just drive in the attractor. Except that the time course that's generated is called here the plan, that is the control. To physically do it is a separate thing. And you will be seeing later that most of the time we're already in the attractor from the very start. Yeah, I think that's all I need to say about this one for now. So obstacle avoidance is just the repeller, right? If there's a certain obstacle that you want to avoid, you just say that direction, I will make a repeller, a fixed point. And then if you're a little bit to the right, you have now a positive rate of change. So you will be further to the right. And similarly, if you're a little left, further to the left, so positive slope. There will be a different reason why this is not just a linear function. I'll come to that in a moment. I forgot to mention, I'm doing something in these plots all the way through the lecture that is a bit different from what is actually done and actually in the papers when you read them. And this is just because of the mental gymnastics that it takes to read these graphs. So as you know, mathematically, angles, the positive direction is counterclockwise, right? These angles are defined in this direction. And so but conventionally, when we plot dynamic systems, the variable goes to the right. That's just the way we plot the dynamics. So we put this to the right. So when I'm going to the right, the vehicle actually turns to the left. So in a lot of these plots, I'm actually flipping that. I'm saying, yeah, I'm going to the right and interpreting this as the vehicle going to the right, even though that's not really true. And so on some plots where I've actually flipped the graph to make that match. So it's just to make it easier to visualize it, right? So if you're confused about that, just always check what the definitions are. So it's just to avoid too much mental gymnastics. So I'll be more specific about the obstacle avoidance term in a moment. And this is a more general thing, that is all these contributions, we call these contributions forcelets. So contributions to a dynamic system could be considered as virtual forces. Now, it's not a mechanical thing here, but mathematically analogy. It's a contribution to a rate of change, I could say, something like forces. And that's because we typically think of them as being localized. That is only around certain heading directions where we actually talk about these forces. And in a way, they're characterized by three things. They're characterized by where the zero crossing is. So that's the attractor or repeller location, the desired or undesired state. we call here specified value. The strength of that, so it's actually strength relative to other contributions, is really the slope. And if you did the exercise, you know that the slope determines the relaxation rate, how quickly you're going to this attractor or how fast you're moving away from it. And then if you have multiple influences, you can see that the one that is deeper will have the strongest weight. It will overpower the ones that are less weak. So that's what we call it strength. And then the range, that's the region in heading direction space in which it is non-zero or not negligible. So I already hinted that the target is often formulated as a sinus function. That would mean its strength is it has no limit. It just has one fixed point where it goes to zero behind you, and that's because you're assuming that you always want to move the target irrespective of where you're currently heading. So you're not losing that constraint just because you're not heading right. While the obstacle wheel will typically limit the range. For instance, if will be moving in this direction, if the obstacle is far enough from on the side, then you don't want to be influenced by it anymore, right? It's not relevant to you anymore. And maybe that range will also be a function of how large the obstacle is. So it's a whole region, then you make it a wider obstacle, so you can turn from its center. You can have to turn further for its influence to decay. Right? In practice, it's a heuristic function. We'll have in the next lecture. I'll have a case where we can actually figure out what the right width is. Here we'll be doing more on this talk, because here the obstacles will be like point obstacles. So these are these three numbers that characterize that. So that's the individual contributions with these three numbers. Now, the simple approach that we're using here is that we just add these constraints. That is, when we have multiple contributions, we just add the contributions and then arrange these parameters such that the right behavior results. And I'll illustrate that here in this case. This is the case where you're not really doing that in practice, just an intellectual exercise. In practice, when we have more than one target, we figure out which target on a different level of representation, a more cognitive one. But let's say these targets would be on the ground and you want to position your robot over these targets. And then you could imagine if there are two targets that are close, you can position yourself on both by just sort of sitting in the middle of them. That would be fusion. And then when they are far enough, then you have to select one of those. And here, a simple illustration how just superposing these two constraints, adding them up. These are now they're just two target constraints, right? But I just want to illustrate that even then there is a possibility to make decisions. And this comes about as follows. So let's say these individual attractors here, again, that's not how we really do it, right? Just for the exercise, because I said sinus functions, right? And then this doesn't work. This would be only if they are narrower functions than sinus functions. So this lila line is supposed to be one of the individual contributions to one of those targets. So it would have an attractor at that heading direction and then have a certain width. Maybe that width reflects on the size of the target. And then the other one would have a slightly shifted attractor at a different location. And I could see that in this linear range, these two functions superpose into a linear function. So the red line is the sum of these contributions. The slope is 2 times the slope of the individual ones. I think it's actually true. It doesn't even look like that, but I think I actually really did that with actual functions. So it must be 2 times that other slope. And it averages. So if both of these have the same amplitude, that would be averaging. And then the peak rate of change is larger, and then it peters out just when these two are out. So this would make a attractor at the average location of these two. Now, if you're mentally pulling apart these two targets so that they are no longer overlapping so strongly, and it will be in terms of this width that what is relevant here for what is not close, then at some point there is a difference. So for instance, if they're far enough so that their width doesn't overlap anymore, then you would have one, the lila here is sort of absorbed behind the sun that goes this way, and the other one only starts here and goes that way. So now you see they overlap very little, and therefore there is a attractor here that belongs to the leftmost attractor, and then there's another one that belongs to the rightmost, and then in the middle there's just a extra attractor, repeller. That is where, it has to go on the other side again, right? It makes an attractor and has to sort of return. And so that would be sort of the decision point. That is, if you're heading a little bit to the right of this location, you would be going to this attractor. See here, I'm using the trick of saying to the right of. Of course, in the end of the book, to the left of, but to the right of here in the graph, right? And if you're heading a little bit to the left of this, then you would be converging to the other solution, right? So your initial heading would determine which of the two you're going to. So this is would be an example where it makes a decision, and the decision would be strictly based on its initial heading. Of course, it would be coming from a longer history where maybe these targets suddenly appear and has to make a decision. Again, we don't really do it this way. It's just the simplest case, and you'll see in a moment the obstacle case is a little bit more complicated, but it's the same idea. So we would characterize that by bifurcation diagram, and you already did in the exercise a simple bifurcation diagram. The exercise was a tangent bifurcation. This is a pitchfork bifurcation. That is, you were keeping track here of the attractors and the repellers at different distances, angular distances between the two targets. And so if the angular distance is very small, then we had the single fused attractor between those two. And if it's sufficiently large, we had the two attractors with a repeller in the middle. And at a critical point, all the three of them are meeting. That will be, if it's totally symmetrical, if you really, the targets have the same function and they're symmetrical, you could flip them and get the same result. And then the three of them have to meet at the same time, in a sense, right? That's what the pitchfork bifurcation is about. So if one of them has a larger range, this would be broken, and you would actually get a tangent bifurcation and another branch that is no bifurcation. That's discussed in the dynamic systems tutorial. We don't need that here. It's just an idealization. So the bifurcation sort of describes, bifurcation is essentially a change in the number or nature of the attractors and repellers, right? And as a parameter is changed. So bifurcation is a property of a family of dynamical systems that is spanned by some parameter. Here, the parameter is the distance between these targets. And it would be generally, of course, sensor information that gives you information about these targets that would lead to that kind of bifurcation. And that's how you can come to qualitatively new solutions. You would come from the fusion to that decision-making situation through that. And very typically, that is actually what would arise as you move. It's not like you're sitting there and somebody changes the world. It's actually the robot moves around, and as it runs, the world as computed in its local sense information changes, and a bifurcation occurs. So, for instance, if you're having some estimates of these targets, as they might look very close to each other when they're far, and as you come closer, you suddenly, the subjective angle from the vehicle point of view widens as frame moves with the vehicle, widens, and suddenly the angle between these two targets from the point of view of the vehicle increases as you get closer. So you would be literally moving here along this axis as you're approaching these targets, and therefore there would be this bifurcation, and then you would switch from one side to the other. And that's actually a reason why it really happens sometimes that you are in a repeller. Now, if you were to do this, you approach these two targets, and as you approach them, the angle increases. You would be really sitting in this attractor initially, and then it's a fixed point, so you would stay theoretically in this repeller. That would be not ideal. And in practice, this will not happen because you're not so precise. There will be some error, some motor error, some sensor error. And we actually, in the approach that we implement, and this is next lecture when I show you the low-level system, inject noise artificially into these dynamical systems to make sure that we don't get stuck in a repeller. You would think, now, why would you ever be in a repeller? Because of the bifurcation, you might actually end up being in a repeller. And you have to make sure that you escape from it. Now, I'll show you an example where you can actually see that, where the robot takes a little time to escape from the repeller after a bifurcation. So it's not totally useless. then this is sort of the subtlety that makes it maybe that not everyone picks up on this approach so much because it requires that kind of understanding. Good. So this is still an academic example because we don't really do it this way because the kind of information you have about sensors already, about targets typically involves making decisions earlier than the motor behavior based on other things than just your initial heading. But it's very real for obstacles, right? And so this is the analogy thing for the analogous problem for obstacles. So here I'm assuming that there are two obstacles. This is where this is a sense plan act thing because I'm saying obstacle number one, obstacle number two is my plan, right? These are objects, and I enter a function for every obstacle. That's based on a plan. When you have sensory information, it might be just noisy data, and it's not clear which is which obstacle, and are there two or is it many sensor readings on the world and so on. That's what we'll talk about next week when it's more like that. Good. So two obstacles. So they make this orange or ochre, what the color is here, contribution. They are repellers, right? And so one repeller lies in that direction. Let's say this is this one, and the other one lies in that direction. Will be that one. The red point is the repeller, and there's a target here. It's behind these obstacles. That's the only relevant case, right? It's easy to avoid obstacles without target, but if you have a target that pulls you into the obstacles, that's where it shines. So we put it here on purpose. So that has an attractor here in the middle, and I'm already indicating here the hierarchy of these different constraints by using a slope that is relatively flat for the target contribution compared to how steep the positive slope is for the obstacle contributions, right? The steeper ones win. That is the priority is to avoid the obstacle, and the target is weaker, and you can control that by the slope of that dynamics. And so the green lights are the green circles here are the attractors. So there is an attractor here in the center, and there are two attractors here on the left. So theoretically, the individual contributions only have these three things, right? The obstacle contributions make these repellers, like there's a repeller here and a repeller there, and there will be an attractor in the middle. But the two repellers of the two individual contributions have, oh, sorry, I got in the wrong slide. So I think this slide was there, right? Sorry, yeah. I must have touched this here. So here, this is the repeller from the left obstacle, from the right, and the attractor in the middle, right? These are the things. This is sort of an emergent attractor, if you want, on the outside. That's meaning going around the whole configuration. Emergent in the sense, you see, you have an obstacle contribution like that. It's sort of like a half attractor, right? If it goes to zero here, and this is a negative slope, so it's almost like an attractor, except that if you're on the right of it, then it's no longer attracting, but it's sort of, he's pushing you out to some heading. If you add just a little bit of attraction from the central attractor, it makes a real attractor, because the sum is the black line here, and then you see it's a real attractor because you have this repulsion from the obstacle plus a little bit of attraction. That together makes an attractor. So this is this one and that one. So that would be going around the whole thing this way or going around it that way. So you have a total of 3 attractors, 2 repellers. The center one is the natural one. The 2 repellers are natural, and then the other ones are the emergent here from having attraction and repulsion. That makes a new equilibrium here on the outside. Good. And now I push the obstacles closer to each other. And again, that could be also just because you're at a different distance. Actually, in experiment, it's the other way around. They are first closer, and then when you get closer, you see that there is an opening. So push them closer together, and that means these 2 curves are pushed closer together, and then inside the same kind of bifurcation I just showed about the 2 targets when they get closer, and then the 2 parallel lines here fuse to a single line at the center with double the slope. It was a negative slope in the previous example, now it's a positive slope, but the same logic. It makes a bifurcation. There's a single repeller left here in the middle that overrides the attractor that the target wants to erect. And then only these outside attractors remain. And so the system will have to, again, escape from this repeller and go around it this way or that way. Yeah, that's again a bifurcation. It has this kind of nature. That's a bit more complex because there are these outside attractors that are there all the time that are just deformed a little bit. Inside there would be a pitchfork if it was really symmetrical, if it's really entering the obstacles symmetrically. Generically, one obstacle will be closer and it will actually do a tangent bifurcation. But in the worst case, there could be a symmetrical situation where it would exactly collide with the two obstacles at the same time, left and right, and that would be sort of the optimally bad thing. It's much easier to avoid a single obstacle, right? And that's why we have to design that right, that it escapes from that kind of situation. That's what leads to this pitchfork, where now the pitchfork is the subcritical. If you read the tutorial, you know that every bifurcation has a supra and subcritical version. That is, you can look at the bifurcation diagram with time running forward. That means you have certain attractors and others are repellers. If you let run time backwards, you do the movie backwards, right? Then the repellers become attractors, the attractors become repellers, right? It just flips. And so every bifurcation exists in these two versions. It's just really writing the whole equation upside down, minus. And so previously these were attractors and this one was a repeller. Now it's the other way around. The outside is the repeller. Just to remind you here, see? Attractors outside, repeller inside. And now it's attractor inside, repellers outside. But it's the same kind of bifurcation here. So that's the bifurcation diagram here that would now be encountered as the distance between the obstacle increases. Now, typically, it would be so in the symbolic approach, it would be the case that that happens when you approach, right? You have two obstacles that might look close, and you would fuse them, and then as you get closer in angle, they will lie further apart. So you would be running this through this in this direction. You have a central repeller, and then it splits into two repellers, and you might be able to, if you're really encountering this, you might be able to go through if ultimately it opens enough, but it's quite possible that you went went around this thing from the very start, depends on the parameter. Now in practice, when the sub-symbolic approach we'll discuss next week, the situation is a bit different because the width of the obstacles also changes as you approach, and the dynamics is more complicated. Good. So that's already the core idea. So that's how bifurcation is all. So multi-constraint satisfaction emerges just from the bifurcation. Now, why do we do it this way? I mean, fancy perhaps. So one advantage of doing this is that we really only need to design the attractors and repellers, and then bifurcation says if the constraints on those change under certain conditions. So we don't need to worry about all the solutions because the attractors and repellers organize the solutions. So from every solution, you're converging to the same. The exercise actually was supposed to illustrate that. You might not have noticed that. And plotting different initial conditions, you always converge to the same attractor, right? That shows that, if you know where the attractor is, it's globally stable, then you can say something about all the solutions. They all converge, right? And the repellers are sort of cutting the space into different subspaces where you converge to one or converge to the other. There are boundaries of basins of attraction. And so just setting the attractors and repellers organizes these solutions. We will later discuss the potential field approach, where the behavior is not sitting in the attractor, but it's actually going to the attractor. And it's much more complicated because now you have to make sure that all those solutions, when you go to the attractor, all fulfill the constraints that you want to fulfill. So that's why this is good and it's convenient. The only thing that is maybe initially a little bit strange is why it's possible to sit in an attractor and behave, right? So why does that do that? And the first answer to that is that the attractor is an attractor of heading direction. Heading direction is essentially a velocity type variable. It's the direction. The velocity of the vehicle is its direction and its speed. Now, there's a vector in the plane, has an orientation and has a length. The length is that other variable that I gloss over, And the orientation is therefore the angular component of the velocity. So it's a velocity vector. And if you're sitting in an attractor for velocity, then you're moving. You're fine. I mean, you're in the car. If you're driving at exactly 100 kilometers per hour, then that's your attractor. Let's say you have a control system where you look at speedometer, then you're still moving, right? And as you're moving, you're getting sensory information about the world that changes because you're moving, right? The world is constant as such, but you're moving in the world, so the sensory information about where you are in the world, distances change. It's therefore the dynamical system that takes such information as parameters changes, and interesting stuff will happen. That's roughly why it's possible, right? If the world is very boring, there are no obstacles, you have just a target, yeah, you will initially go to the attractor and then you will just go straight. That will potentially happen, or you can do road following also. You can imagine just the direction along the road is an attractor, so you will always just go in the direction of the road, and that's perfectly boring unless you have to avoid an obstacle or some trivial constraint. Here's an illustration. This is where I play that trick with this mirroring that illustrates a little bit that sort of situation. So it's just two snaps. This is actually taken from real robot data. That's why these curves are a little odd. And so the robot was initially sitting in a certain position where the target was here a little bit to the right of this obstacle in angle. And it was heading here in this direction. And see, here's the target. Lila is the target contribution. There's an attractor here. Again, I flipped it here. The obstacle is a little bit to the left of that positive slope. Here, the sum is a green function. Sorry, the color code changes all the time. So you see there are two attractors here. An attractor here a little bit to the left of that. That would be going around this way. And an attractor on the other side, which would be going around it this way. And there is a repeller here just in the back, right? And so in the back, there will be another decision between these two attractors. And so the vehicle is initially heading, is essentially in this attractor. It's a little bit to the left of that thing here, right? And therefore, it will be moving in this direction. So sometimes later, it's in this configuration. It actually turned away a little bit and for reasons that come from this obstacle avoidance. And so if you now look at this situation, now the target is a little bit to the left of the obstacle in angle, right? Just because the vehicle moved further, so the bearings change. And there you see here, they flip position here. It's just for you to orient. It's not so important per se. And there's only one attractor left, which is keeping going in this general direction a little bit to the left. The other attractor is pretty much disappearing right now. It's just touching. This is a tangent bifurcation, right? It's just touching. Will be gone in a second. So in other words, the other direction of going around here becomes unviable. I can imagine why that's the case. So again, next week I will show you live data from the slow level approach. This is when it's really discrete things. And so that gives you a little bit of sense of what's actually happening, right? It's always in the attractor. The attractor is moving because it's moving on. I mean, it's moving here only because there's some interesting stuff around. If there wasn't any obstacle, it would just go straight to the target. There's nothing interesting happening. But because there's obstacle, it forces it to go around. And as it goes around, the landscape changes. And then the vehicle makes this interesting behavior. You can see that this also ultimately determines the limits of that. And here, it's again symbolic. We're assuming it knows the world. As you can imagine, if the attractors move too fast, it can't stay in them, right? It will be always closed. I mean, the attractors move, and it would be tracking these attractors with the relaxation time, how steep the dynamics is, and that has to be something that is tuned also to the control, that you can actually achieve that in control. So it has to all be adjusted correctly. On our robots in practice, it was often the numerics that was the limit that we had to get the sensor information in time. And therefore, you're not allowed to, you can't really tolerate changes of the dynamics that are too fast. Then it's no longer, you're not in the attractor. And that meant that we had to put a speed limit on our robots. And some of our robots, actually, the robot would be able to move much faster, but because of the sensor information in our implementation, we needed to go somewhat slow so that it could actually do the computation. This is like 30 years old, right? Today you could have, this is much better sensors and much better computers, so you can go as fast as you want these days in practice. So for instance, this is true for humans too, right? You can avoid obstacles usually. If you're in pedestrian, you're avoiding pedestrian. Sometimes there's some question of whether you want to avoid collision. But if I shoot a bullet at you, you will not avoid it, right? So there's an intrinsic time. It's just too fast for you to perceive and generate. Unless you're Superman, you can't really do that. So that's a constraint for the speed at which you're going. So we already did implement that, and just to show you a little bit the complications if you do it this way. This is a very long time ago, in 92, when my doctoral student Joseph was now working in this company here at the end of the campus, the company that was founded from the institute. He did his doctoral thesis, and this was the robot. It's like a 1 meter long, this huge thing, a very awkward, terrible programmer interface. This was the computing, which used some kind of parallel computing. So a lot of effort at that time to just get that. And it had so its perception of the world, this was one of the bottlenecks. So perception of the world was based on a special method where you have a stereo camera system. You can actually also use one camera at different moments in time, but we had a stereo system. And you're projecting the images from the two cameras onto the plane. You have to know how the camera is mounted onto the plane. And so you're drawing on the surface the image that you would need to get that image into your camera. And that's a different image from the left and from the right. And the difference arises from anything that is not in the plane. So you can have a detection of anything that emerges from the plane. It's a kind of cool approach. Someone got a patent for that. Was never then used because better sensors arose. This would be just with vision sensors. So in any case, so that's how it was done. And it had a idea about the target position from that reckoning that is from a map. That is, would really, you would give it its target in terms of its initial position, like 3 meters to the right. And then it keeps estimating where it is and makes errors as it does that. And that's very typically how the target acquisition works in most systems. But like these deployed systems of vehicles, it's actually cool in the Augusta hospital. I had to go there recently. They have autonomous cars like that. And this also, they recalibrate when they do obstacle ones, they're just slowing down. And it's very limited. But it does that, and it keeps integrating where it thinks it is. And pretty good motors, always smooth surface. And then it has some calibration points, and they actually have some markers. So it's on the ground, they detect where they are to reset the coordinate frame every now and then. So that's also done for target acquisition. This is sort of an image of how that happens. So the goal is given in this way, computationally, and this is initial position. And these little things are sensor readings where it thinks something sticks out from the ground. So in this approach, we actually had a whole level, what we call of representation, where we grouped these things into then object-like things to enter them into this approach. And the way we did that was dynamical field theory, which some of you know who took the winter, maybe only one person here. They did the winter semester course, which is the modern version of that. So we developed some of those ideas then. That's a neural theory of how you would do that grouping into objects with peaks. I'm not explaining that here. Good. And so again, this is what I said initially. This is in that sense symbolic, that we have these different contributions to the dynamics that even continuously over time that you keep track of, right? As the vehicle moves, it still thinks that this group is one obstacle and that group is another obstacle. So it's not actually totally trivial to do that and to have that kind of information about the world. We call it symbolic, so maybe not right. So next week, I'll show how you can do the same thing in the behavior-based approach where you are just taking raw sensor information. But before we go there, so this ends that part. I want to show you a human experiment that essentially does that sort of thing. It's really interesting because I gave we would develop this in the 1990s. You saw that 92 was one of the papers. And I developed this because of my previous work in so-called ecological psychology and human movement behavior, but not navigation behavior like that. But the principle, that's called systems thinking, where there is an idea that that's a principle, that you have table states, that you get flexibility from bifurcations and all kinds of things that I might even lecture a little bit. I have this timing module. If I can get to that, I'll show you a little bit that work on coordination. And so by analogy, I postulated these kind of ideas. And then Bill Warren, who's the lead, the senior author on that paper at Brown University, invited me to the lab because they were just setting up a virtual reality cave, one of the earliest ones, where they were interested in studying how humans locomote, right, and navigate. So it's how they move in the plane, right? It's not about their legs and so on. It's how they move in the plane. It's also not so much about ego position estimation. It's just some structure in the environment. They used virtual reality. I don't know exactly why they did that, but it certainly enabled them to control the environment at every moment in time, right? They could turn on a target or on an obstacle, and therefore it could make controlled experiments like that. I was actually there. I gave a seminar about this method, and they used these models to fit their data. Very cool. It's like huge. These you have this. At the time, you had. I think it was already with a screen here, and then they track where you are, and it's a large hall, so you can really walk without running into the real world, right? Which is very awkward. Yeah, and so the kinds of things that they did is they had participants start in a certain place, and then people would start walking. They have some instructions about keeping your walking speed constant. People are quite good at that. And then in different experiments, different things happen. So in some experiments, a target appears suddenly. A target is like a cylinder, it's like has a certain color that appears in a certain direction. They could control in which direction it appears and in which distance it appears. That would be one experiment. And they are asked to just walk to the target, right? And this was good. They see how they turn. And this is the superposition of these different things that happen here. So this is the turning rate as a function of the heading direction. The heading direction is now centered in the target position. It would be a really different curve, right? But they all just shift the heading to be centered in the target direction, so that now the initial heading compared with the target is the variable. And you see that it has overall this attractor shape, right? This has a fighter versus one has the attractor there. It has, so if it was a dynamical system of our nature, it would actually, you couldn't have these different curves, it would be just one curve, right? And so there's a little bit of a discrepancy here that ultimately comes from the fact that they are already, so that the target appears abruptly in a sense, right? And so you could say there's another process of getting to the heading that would correspond to the dynamics when you have that target. So if it had been visible from the start, you would be on one of those curves, maybe the outermost one. And you could say this is like getting to that curve because now suddenly the target appears. They also vary the distance. You see the distance essentially affects the slope or the largest excursion, and ultimately has to do with the slope. It's different coming from the left or the right. So it's the same kind of curve, and the slope is varied by the distance. If it's close, you turn sharper. Makes sense. The second experiment, they did a similar thing. They walked to a goal at a certain distance, and then as they walk, an obstacle appears. Obstacle is also a cylinder with a different color. And then it appears at different angles and different distances, and then you get these kind of curves. So this is where the obstacle would be, and they're only showing now the data when it's on one side, and you can do this, the other side, just flip that around. And so you see it's a zero crossing with a positive slope, and sort of a fall off here, very much like the dynamics. Again, the different initial angles lead to slightly shifted curves, and also when the distance is a slightly different curves. Because it shows up when it's very close, you have the steepest sequence excursion. And so they modeled this with our model using these heading direction, obstacle, and so on, all the same math. And this is the results from the model. So so that is right. This is not exactly the model I'm showing. It's a model that is slightly different in that it has a additional term. So if this is 0, you put this on the left, then it is the dynamics I'm talking about is phi dot. This will be the target term, so this would have a negative slope, and the exponential is some form of limiting the range of that. And this will be the obstacle term, and there will be some range limiting function. And there are parameters here that are dependent on the distance and on some angular range factors. And these are, I'll show them next week, these are really the same terms that we had in our robotic example. We didn't really explain how the equations look here in this case. And so by making it second order, what they're doing is essentially giving it an inertia term. So it is something that it takes a little time to go to the state that would be specified by the current attractor or repeller solution that leads to this behavior. And in the exercise I'm going to put out, I'm essentially inviting you to study this dynamics in 2 ways. That is, you essentially to see how it's connected to our kind of equation. So one is this adiabatic elimination, when you say, if I neglect the inertia, so I'm making it a very non-inert system that can instantaneously turn, then I get to the same equation. And the other one is to just do this as a dynamic system with 2 variables, phi and phi dot. So it's like a second order differential equation, right? That has 2 variables. And then you can do the analysis in the plane. So fixed points in the plane, you can try to understand that. So that's also just to make you, no, I think this is actually one exercise down. Yeah, sorry. No, it's not this week we're doing something simpler. Exactly, it's going to come later. So the upshot is this is consistent with the dynamics that we're just looking at. It just has this inertia term and behaves in the same way. Yeah, good. And this is sort of an interesting kind of side effect of that. Then they had one condition, and this is the model. So one condition where they, again, start the same way, and then the target comes on. I don't remember if the obstacle comes on at the same time or which one came on first. Don't remember that. But in any case, they had a condition when the target was sort of here, people would go around this way, and then when the target was there, they went around this way. I think the target comes on later. That's how this came about. They're kind of, this is a model, and this is what it looked like in the experiment. You can really, this is the model and the experiment. Yeah, it's not directly plotted this way, but you're essentially, from this reconstruction, you're seeing that that's exactly what's happening, that they are, depending on the distance of the target, they're going this regime where they turn first right and then left, and the other cases, they are going around it the other way. So it really describes that. Yeah, good. Yeah, so it actually really describes the human behavior. And so this lab has since done, I don't know how many, dozens of studies where they use this math, and they are essentially doing now, swarm behavior, humans, groups that go, corridors, different directions, and there's this whole traffic physics. And you know this in Duisburg, Michael Schreckenberg is actually an old friend of mine from ancient times, and we were both still physicists. And he has developed traffic physics. He's not using exactly that, he's using a more macroscopic level. This would be, they call that the macroscopic level, where you're describing the individual pedestrian's behavior. And that's what Bill Warren does. And they do this more macroscopically. They drive essentially pedestrian or car traffic, like hydrodynamics, like a density function, stuff like that. And they have, for instance, predicted these shock waves that you have in cars. There's a second group, Helbig, who's now in Zurich, who I don't know who invented which, but they both work in similar directions like that. And so, for instance, here in the A40, this so-called Schnellweg, even though it's not very fast, often there's a lot of traffic jams, and they had it instrumentalized. I think the measurements, the device is still there, but no longer functional. So on every bridge and any of these signs, they had measurement devices, and they would be able to construct the flow from that, and then were able to show that these shockwave dynamics really apply. The shockwave dynamics essentially, when there is a slowdown point, then there would be the density increases, because when density increases, the average through flow decreases, the capacity of the road decreases, and that amplifies that effect. So it's the self-amplification of the effect. And then we're able to use these model equations to predict under which density conditions and velocities and so on this arises. So one of the measures that are taken in a lot of places are to minimize perturbations. These shockwave arise when there's perturbation. The perturbations, for instance, cars entering, and you know here in the Ruhr-Schnellweg, they have this, I still use this name, Ruhr-Schnellweg. They have these, the access ramps have this limitation that only one car at a time. That flew out of that kind of research. And there are experimental labs that did things like that in the US, where they had people driving like in a circle, and then they would really like provoke that kind of situation by inserting too many cars, and they would really observe the shock waves. So if you're a driver, the way to minimize shock waves is to be a low-pass filter, to smooth, right? The stupid thing a lot of people do is, if it accelerates, then accelerate to quickly fill the gap. But no, you should actually low-pass filter, that is, allow the gap to fill, and then when there's density increase, you don't have to brake as abruptly, and that can sometimes prevent the shock wave from forming. Not always, but people are worried about people getting in the lane and so on. So it's very irrational behavior, because the shock wave reduces the capacity of the road enormously. Yeah, so that's a whole line of work. So this is the micro level. They didn't study that. They also did human pedestrian flows with this macro level. Schreckenberg got a little bit of trouble because he was an advisor for this party there in Duisburg, where there were people died. Remember this? There was an outdoor festival, and there was some disturbance. I think it was some blockade or something. I don't remember. And then people were panicking, and then some people got crushed and so on. And he advised them on this design. But probably it didn't really. It was just some very qualitative thing. But then somehow it was, it's your fault or something. I don't know exactly whose fault it ultimately was. What a bad design of the escape routes, or something was blocked or whatever. So this sort of thing of analyzing designs, like evacuating a cinema, evacuating cars, are now routinely done with models beforehand. You also do field tests, which are very expensive and difficult, but you also try it before, and you have some models of the individual's behavior. The models that are done for these sort of things are much simpler. It's like a point. Every movement is a point. There's a certain forces acting on the point, like distance from neighbors and having similar velocity, and then they get these kind of flow equations. But then there are these people who do more microscopic, and that's the Warren lab, where they are now looking at things like configurations. I actually just forgot now their main story is, but they do this really comparing to individual trajectories of people out in the wild. And there's a lab in UPenn, actually, I think it's no longer, it was in the early 2000s. Someone called At Large and Gulshina Baishi. She might be still there. Actually, she's quite old now, but the American professors never retire. They had a lab where they did collective robotics. So they used this approach to organize how many robots cooperate. And they were treating each other as targets, that how they could move in configuration. And so the hindpoint was when it was in configuration and an obstacle would arise, they could sort of break the configuration to the obstacle just by the slope being steeper for the obstacles, and then reconvene into the configuration without any, it's just this kind of dynamic. So without any like meta recognition or anything, it's just everyone just sees the other and does that. And finally, my former student, Estela Bishu, whose work I'll show next week, she has a lab in Portugal, actually one of the students currently in my lab. And she developed a whole approach to individual robots. It was typically two robots that would cooperate, like two robots that would transport something, and like no, it was just a demo, but they work also with Bosch, I think, with a company that has production there, Bosch or Grundig, I think, in Portugal. And it was Bosch, and they in the factory floor they have two robots that transport something, and they have to avoid the obstacles together, so that they not one goes around it one way and the other way, and then the thing they transport would get stuck, right? And she developed a very ingenious way of how she added additional constraints like via points for the robots, and the follower versus the leader robot, and the follower has different dynamics to the leader robot for that to go around. And that is it's a quite elegant solution in that it's, you know, the sort of low-level stuff that we're talking about here. And it doesn't need any floor plan or a big time plan of the obstacles on. When you do this classically, you would have a mathematical model of everything, and then you use one of those polygonal planners to do that, and it would not be easy to deal with that in real time. And if something shifts, would have to replan and so on. So it's a much lower level kind of approach for that. So there are some outflows of this work. Yeah, actually, there's more, but there's some people also who use this for animation. So like to have movies where you have a lot of stuff moving, and rather than animate, meaning you yourself writing or programming, every next frame, they had equations like that to let different obstacle and people move around, and then they have some rendering and so on that, right? So I only know the academic work. I don't know if in practice somebody uses that, but there were publications about doing it. So that's all that in that symbolic style that's done. So next week I'll show you the sub-symbolic version of that, and I put out an exercise sheet. I uploaded today. Again, same thing, turn in on Wednesday, which is just a opportunity to look at one term. It's the obstacle avoidance term of these equations, and to understand a little bit, what it does and how it depends on parameters and so on. It's again using math and to create a intuition for what it does. And a week from now, I might do the one that I hinted at, the pedestrian. Good. That's closes this lecture.